crystalline solids. We've mentioned crystalline solids before and said that they have a long-range order to their atoms or molecules. Many of these crystalline solids are just plain beautiful. Here's an example of a crystalline solid, a mineral formation that you might find. Here is an excellent photograph of a snowflake. And ice makes a crystalline solid. And the reason that we have these shapes on the macroscopic level that are so geometric and pleasing to the eye are because of specific structural patterns that the molecules and atoms have. So when you go down into the molecular and particulate level, you see there's this particular order, and that order affects the macroscopic shapes that these solids have. So how do we figure out what the structure of these crystalline solids is? We use a technique called X-ray crystallography. So what they do is they use electromagnetic waves, which we have studied, haven't we? Electromagnetic waves, and these can interfere with each other, and they can cause constructive interference or destructive interference. And as we saw before, when you pass light through two slits, if the distance between the slits is similar to the wavelength, then we're going to get interference patterns as the light bends through the slit and interferes with the waves coming through the other slit. And so this is the basis of X-ray crystallography. The spacing of the atoms within the crystals are about 100 picometers, which corresponds to the wavelength of X-rays. So we can shine X-rays on these crystals, and the crystals act as the slits. The atoms in the crystal act as the slits and cause diffraction patterns. From the diffraction pattern, we can learn things about the geometry of that crystalline lattice. So it gives us information about spacing between the planes of the atoms. We look at this illustration here, and like here there's three blue atoms in a row. That forms a plane. And if you're passing X-rays through here, it can go between the atoms, and that will act as two slits and cause interference patterns. So here we're looking at atomic planes. Those are not airplanes with atomic bombs or anything like that. They're just atoms that happen to be in planes, flat sheets. So here's a row of atoms, and here's the row of atoms beneath it, and they're organized, they're crystalline. Well, when two waves come in, they're going to bounce off of these atoms. And if these come in phase, if the waves are in phase, they're going to have constructive interference. What happens here is ray 1 travels this distance, ray 2 travels a larger distance because it's going into this crystalline structure, and we can find this added distance that it travels. So the path difference for these two guys is 2a, because it's going this much farther here, A, and this much farther there, because it's shifted over. So the path difference is 2a. Do you want to go through all the geometry of this, or just look at the final result? We don't need to, no. So this is all geometry, trigonometry, angles, and such. The bottom line here is n lambda equals 2d sine of theta. So theta is the angle here. Lambda is the wavelength. What do they define d as? I don't remember what d is. That's fabulous. The diameter, thank you. Yes, the diameter of the atom. There it is, labeled right there. Thanks. So we can look at these waves when they come out. If the difference in path lengths is an integral number of wavelengths, then they will still be in phase when they come out, and we'll see constructive interference. And so how does that work? Well, if this goes an extra one wavelength here and one wavelength here, they'll still be lined up when they come out. If this goes 0.3 wavelengths and 0.3, when they come out, they won't be in phase anymore. And so n is just some integer number. That distance is 2d sine of theta, where d is the diameter of the atom. And so we can learn things about the diameter of the atom and how they're arranged by looking at the interference patterns. So typically the angle that produces constructive interference is measured. So they're going to measure theta, and then they'll figure out the distance between the atomic layers using this equation, which is just a rearrangement of Bragg's law. I should have said that's Bragg's law. So they've got a wavelength of light, and you can control that, and you can control the angle that you're shining it at. And you can rotate that so they'll vary the angle and look for constructive interference. As you can see that, the light and dark patterns change. So at an angle that gives constructive interference, we know that the distance between the layers is equal to some integer number times the wavelength over 2 times the sine of that angle. So by finding multiple angles where the interference is constructive, we can actually figure out what the d is, the distance between them. Yes?
When it says it's used for simple atomic lattices and proteins, what is meant by simple?
We'll get into that.
Okay.
Yeah, we'll get into that. We'll talk about several different atomic lattices. They use this for determining structures of proteins. This was important in determining that double helix structure of DNA. That book I was listening to earlier this summer. He wrote this article about investigating the history of Watson and Crick and their studies on the structure of DNA. And there were actually two other people who were also working on this. And X-ray crystallography data actually was the final key that got them onto the right track. So we're not going to learn how you would actually do this, but we're just going to learn how to do some of the more basic calculations. So if the spacing between layers of molybdenum atoms is 157 picometers, calculate the angle at which X-rays of 154 picometers will produce a maximum reflection for n equals 1. Oops, darn it. Okay. The spacing and the diameter, the spacing between the layers is d, yes. So d is equal to 157 picometers, and lambda is the wavelength, is 154 picometers, and n equals 1. So we're supposed to look for the angle. So let's see if I can remember this. N lambda equals d sine of theta. Did I get it right? 2d sine of theta. Thank you. This is one of those equations that I do not use except in this part of this class, so I have a hard time remembering it. So that's Bragg's law. So we're asked to find the angle. So we need to rearrange this and solve for theta. That's what we're trying to find. We're given n, we're given lambda, and we're given d. We need to find theta. So remember that sine is a function of the angle, and you can't divide by a function. Okay? So let's first separate sine of theta. I shouldn't have boxed that. So let's divide this by 2d and divide that by 2d. The 2's cancel, the d's cancel. Now we have the sine of theta is equal to n lambda over 2d. So what we're going to do is we're going to put our numbers in there. Lambda and d are both in picometers, and so those are going to cancel out. That's just not going to fit there. I'll just go back over here. Sine of theta equals n, which is 1, times the wavelength, 154 picometers, divided by 2 times the distance, 157 picometers. And you definitely need a real calculator to do this. So 154 divided by 157 divided by 2 equals. So we get 0.4904456. I'll just write that down, although we don't really need to do that. There's going to be no units on that. How do we, that's the sine of theta. How do we find theta? The inverse. On your calculator, usually on the same button as sine, is sine to the -1. That's the inverse sine. So you've got this number in your calculator. Just do inverse sine. And I'll have to go up here because I'm not planning ahead well today. Theta equals 29, and it's got a whole bunch of digits. When you're dealing with sines and cosines and stuff, significant figures get a little iffy. We'll just go with the same number we started with. So we started with 3, so we'll go with 29.4 picometers and call it good. I'm sorry, yes. That's not picometers, it's degrees. Oh my goodness. So theta is 29.4 degrees. So using this particular X-ray on molybdenum, when you get to an angle of 29.4 degrees, you're going to expect to see constructive interference on the pattern that comes out. And as you move past that, it will become less constructive and more destructive. And you can go through angles, and it'll be constructive, gradually to destructive, back to constructive as you change the angle. Any questions?